Hi guys, and welcome to the chapter before last chapter, basically, of this class. We are doing chapter 43, and we started it actually last time when we started talking about the structure of the nucleus. And we're going to finish it hopefully today. Then we will start chapter 44 on Thursday. I'm hoping to finish everything, all the content in terms of this class by Tuesday of next week, which is May the 3rd. We may basically keep some stuff for Thursday, which is May the 5th, but then we still have another week, basically. We still have May, not really another week, because May 12th is already scheduled as exam 3, which brings me to another important point, and I followed up with or actually I sent an message to everybody, that there is actually a final for this class. This is a requirement for this class. And I was thinking about something else last time when I mentioned the fact, the idea that there will be only exam 3. No, there will be a final also, which is comprehensive. And we're going to talk about how the format for that exam and how it's going to be. So in terms of major assignments that we still have, in addition to the fact that we need to still do finish the homework assignments, you still have those quizzes that are lingering, and they're due the last assignment. There will be nothing past May 13th in terms of submissions. So in terms of labs, in terms of quizzes, in terms of all of the assignments that are required, then you still have exam 3, which is May 12th. And then you still have that assignment post-test that is also required that we have to do. And we still have the final, which is scheduled for May 19th, which is the first day of the scheduled finals. And as I was saying, it's going to be a comprehensive exam. And I will talk down the road, basically, as we progress on the format and the way to go and prepare for it, because I think it's really contained within those exams that we are going to be, 2 of them already covered, okay? I am still not done. I mentioned to one of you earlier that I'm still not done with grading exam 2. I think about half of you have received the mark on that exam. You should be able to see it on Canvas. The others, I'm still finishing them. I'm hoping by the end of the day today, everybody will receive a mark for that one. There is a common theme though, and it's important since we're talking about the final, that I noticed in terms of this so far, the people that have graded so far, hopefully the other half are going to be better at it. Namely, when you have a single slit experiment, and this is part of physics 2, this is not something that we really went in detail for in physics 3, because it's really the scattering of electromagnetic radiation using the single slit experiment. And that is similar when you run electrons instead of photons, basically. That's what you did with physics 2. So in this exam, you have photons coming super fast on a single slit. And then as they come out, they're going to have dark fringes that form on a specific angles, okay? For this exam, they were a few degrees above the above and below, basically the central point where they're supposed to come constructively, okay? And then the question that a lot of people basically so far I have seen struggled with is, what is the maximum number of dark fringes you're going to see, okay? So let me share, because I'm sidetracked a little bit because it's important, it's on my mind, so I really don't want to lose track of that point. Okay, so that you guys can if in case something similar happens in another exam, because we still have another final and potentially questions like this might come up. So here is the relationship for the dark fringes that form, basically when you use the condition that destructive interference will happen when half of them from the bottom meet the other half of them from the top at exactly half wavelength. Basically, they will be out of phase. So there is destructive interference. It's very hard to argue for constructive interference, but you can simply make the case that between two destructive patterns, there is a constructive one. And so basically here is, so the central fringe is always bright, and it's the biggest one for the single slit. Then there is a region, and then there is a dark region in here. Okay, that's destructive interference, and there is another dark one in here. So between these two, there is a bright fringe. So there is bright fringe in here, similar to this one, although it's a lot less dim, less bright as this one. And then potentially a third one, dark one also, and there is another bright one, and so on and so forth. The question was, under what is the maximum M that you're going to see in here? How many dark fringes you're going to see? And that some people struggled with this one, at least a lot of people I've seen so far. So this is from physics 2, as I was saying. The condition is sine theta need to be no more than 1. That is properties of the trig functions. So if you solve for sine theta from this equation, it's m lambda over a need to be no more than 1, okay? Which gives you then a condition in m that should be less than or equal to at most a over lambda. And this is where optics, geometrical optics and wave optics basically clash in this condition. So in other words, if the wavelengths are of the order of a nanometer for light, okay, few hundred nanometers for light. So this A better be greater than those, because if it's less, if A is less than lambda, if A is more than lambda, no, less, what am I talking? How can I make this fraction bigger than 1? Less than, yeah, you're right. If A is less than lambda, then in this case, M is less than 1. So there is no dark fringes whatsoever. So if A is very small, smaller than the wavelength, then in this case, the beam as it comes out spreads throughout everything in here, and you're not going to see any dark fringes. So the pattern will not form. So the light will be completely diffuse, okay? And if A is greater than lambda, very big compared to lambda, then M is a huge number because it's something, let's say, for example, is less than 100, okay, or less than 1,000. If A is a micrometer, for example, and lambda is 500 nanometer, or lambda is 500 nanometer, or 0.7 times 10 to the power, no, nothing. Let's make it a millimeter, which is a physical, about the size of the hair. If the slit is about the size of the hair, if it's of the order of a millimeter, and this is 0. Times 10 to the power 6 meters, and this is of the order of 10 to the negative 3, obviously 10 to the negative 3 divided by 0.5 times 10 to the negative 6 is of the order of 10,000. So that means M is less than 10. What that means is you have so many dark fringes after the first central one that you don't see anything. You see only the central one. So at this time, it comes out straight out. Okay, the light beam from the light is going to straight out come out, and this is what geometrical optics was. This is where the stuff with the reflection and refraction and all of those things that you did from before. In other words, you don't see any interference patterns whatsoever. You see just the central beam. If it's too open and the beam comes out, it's going to come out from the other end, and that's the end of it. Okay, so this is geometrical limit. And this is actually, the other one is completely blown all the way through. You don't even have a single dark fringe. Whereas in this one, and here you have so many of them that they cancel. You don't see anything. It's all of them are dark, basically, with the exception of the central one, which always has to be bright. Okay, so for the other condition, namely for when you solve this equation for the problem, for the case of the problem, some of you probably will find M to be less than 3 point something, or M less than 2 point something, or M less than 4 point something. That means the maximum number of dark fringes I can form is 3, or 2, or 4. And I actually can find what the angle is for that. So if M is equal, the maximum M is 3, I can go back into this equation and find theta. Because then this is 3, lambda, you computed it, A is given. So from here, you solve for arc sine of 3 lambda over A. Again, this is not really physics 3 per se. This is physics 2. where the limit, the boundary between the geometrical optics and also wave optics, where you have interference patterns and things like that. Does this make sense to you guys?
Yes.
Yes. Yeah. The only thing is, this is a requirement really. M is less than or equal to A over lambda. That's the number. That's an integer. So if you find the fractional number in here, ignore the point after the decimal point. Just because M is an integer less than, let's say, for example, 3.5. Who cares about the point? 0.5 is not an integer anyway. So you're looking for the maximum number. In this case, is going to be 2 or 3 or 4, depending on your problem. Okay. So this is just a sidetracked a little bit outside of the of this chapter 43, because this is way back in chapter 38 or 39. I don't remember exactly which one, but that's because it ties into stuff that you did way back in chapter 36 or 35 when you did wave optics and the discussion of how and when to apply wave optics versus geometrical optics. Anyway, so we're still continuing with the stuff that is related to chapter 43. So basically, so far we discussed the nucleus, and we saw that the nucleus, there is a stability curve for them, and somehow that the ratio of the energy per nucleon has this pattern. For most of the time, it's anywhere between 7 and 8 mega electron volts per nucleon. Okay, so this is in the nucleus. Seems like it stabilizes or it reaches its maximum around 56, A equals to 56, the mass number basically equal to 56. And just to, as a refresher, so that we are on the same terminology in here. I know I wrote this formula and I'm going to come back to it because it's a mouthful thing to remember. So I'm going to come back to it. So something that to remember in here, we have isotopes, and I'm sure you have seen this concept before, where Z is the same, meaning it's the same chemical material. Remember, A, the mass number, is the number of protons plus the number of neutrons. So when Z is the same, we call those two materials that have the same Z but different ends, they're isotopes, okay? Like carbon-12 and carbon-14, and they're both carbon, okay? Both of them have the same protons, the same number of electrons. There is another word that you might see, and that is isotones. Isotone, as opposed to isotopes, have the same N. N is the same. Obviously, in this case, the mass number in both cases is different because Z will be different in this case. So these are two different chemicals, okay? They have two different elements on the periodic table, not the same element at all, but they have the same number of neutrons, okay? So this is another word that we use extensively in this case. So we want to model, we want to understand the nucleus. We want to see what makes it work. We know that there is a force that must be stronger than the electrostatic force to balance, to overcome the electrostatic repulsion. Because remember, you have protons inside the nucleus. So if the nucleus, I can think of it this way. So this is the nucleus. Then it's made up of small particles, nucleons, and each nucleon has its own mass and its own basically properties. At this point, at this distances, at this forces, the force of gravity does not come in at all. I mean, we don't understand what its effect is, and we tried to squeeze it into this model, but we couldn't. Anyway, so the point being, you have a bunch of particles in there called nucleons. Nucleons stands for both protons and neutrons. So some of them are positively charged. And some of them are neutral. Some of them have a Q equals to 0, namely the neutrons. And some of them have a Q equals to positive E, and those are the protons. Well, the protons are very close from one another, and they experience the Coulomb force, which is given by E squared over 4 pi epsilon naught times the distance between them, the distance squared. Yes, that's the force, but I'm looking at the energy. So the energy is E squared over 4 pi epsilon naught times R. So this is the potential energy. And it's a repulsive force because both charges are positive. So this tends to basically break the whole structure apart. So we needed a force that is stronger than this and to account for this one. And that force is exactly what is known as a nuclear force. Nuclear strong force, as opposed to another force that we're going to explore down the road. Nuclear weak force, okay? So this force acts at extreme short distances of the order of a femtometer. As a matter of fact, it reaches its strength, its most strength, at exactly 1 femtometer. If you bring the nucleons closer than 1 femtometer, actually it becomes repulsive. So it acts, it doesn't want two nucleons, it doesn't matter, protons, or neutron. So if you bring them closer than 1 femtometer, this becomes repulsive. If you push them apart, slightly further apart, like for example, 2 or 3 femtometer, then it becomes 0. This force drops to 0 practically. Around 1 femtometer, this is stronger than the electrostatic force by a factor of 137 times stronger than this one. So this is the properties of the nuclear force as we know it. And it's the strongest force that there is. There is no other force stronger than it. So it's really the one that is responsible for gluing the nucleus together, for keeping it together, okay? That's basically what this for, the one that is keeping everything together. So obviously, the more nucleons I attach to a single one, the stronger it becomes, because I bring it more and more, as long as I put them very close from one another. But then this nuclear force, that's what the model comes in here. So it's proposed by Mr. Gamow, George Gamow, who was a Russian dissident who tried many times to escape from Russia and finally succeeded. There are a lot of funny stories with him. At one time, he was caught with vodka and chocolate trying to escape Russia with his wife, and they were caught by the Russians. Anyway, at the end, he succeeded and he came out, and he's one of the funniest people, I mean, in physics. I mean, he's got all kinds of jokes. Anyway, the point being in here, he proposed this model. And the model is based on called the liquid drop model. Think about it this way. If you take a liquid, for example, water, okay, and assume gravity is not there. So it's just suspended without gravity. So in this case, there are attractive forces inside the water, and those forces are the van der Waals forces due to the polarization of the molecule, the water molecule. So they will attract one another. So this is similar to the force, the nuclear force that we're trying to discuss in here. But then you reach the surface, and the surface in this case, you don't have nucleons outside. You only have nucleons from the inside. So this tries to then stretch on the surface, because if you are inside, well, you have enough materials to connect from each side and you don't have a problem. So in this case, all the nucleons attached to that nucleon, and if you go to the next one, it's also attached to this one and attached to more nucleons from outside. So inside, it's purely beautiful. It works fine, okay? And it's attractive, as I was saying, because each two nucleons close from one another, they're pulled together, and that's fine. But then when you reach the surface, there is an imbalance in here. Yes, this one is pulling on this one, and this one is pulling on this one, but there is nobody in here or nothing in here to pull on it. So in this case, it's trying to flatten the structure. Instead of having like a drop, it's trying to pull it together, like the surface tension of a liquid. So the same force that is responsible for putting everything together at the surface, it becomes actually negative force. It's not helping, it's destroying. So this is where the first term comes in. This is actually coming from the nuclear force. And let me explain why that is in here. Obviously, this one grows with the volume. The more you have, the stronger the structure is going to be. Okay. So this is the term that you have in there. And the volume, if you guys remember from the expression we discussed last time, is proportional to the radius cubed. It's something times radius cubed. I mean, it's 4 pi over 3 times the radius cubed, because we are giving it a spherical shape. Okay. So we're assuming somehow the nucleus has this, it's like this particle in here that I have in my hand. Okay. So it has a spherical shape. So in this case, and the radius, if you guys remember, we argued for it to be something R naught, which is a constant that seems to be all the way throughout, because the density of all of the nuclei seems to be fixed. So the radii then are proportional to that constant, which is 1.2 femtometer times a to the power 1/3. So when you cube a to the 1/3, it's going to be a. So this term in here is the volume term. This is the one that is actually gluing the whole. This is the one that adds to the stability of the nucleus. But that's not the only term. This one is trying to destroy that spherical shape. Let me explain where the 2/3 is coming from. Obviously, this term is proportional to the area. The bigger the area, the more it's trying to flatten that surface. It's not letting it to be a spherical. So this is where that term is coming from. It's coming from R squared, because the area, remember, of a sphere is 4 pi R squared. And R, if you guys remember, and I know I wrote it somewhere in here, is R naught times a to the power 1/3. So if I square that number, it's going to be 4 pi squared times R naught squared times a, which is to the power 1/3, but squared. So this term will become proportional to a over 3. So the second term is due to the surface tension. So this is the surface tension. And it's trying to take away from the energy. It's trying to not keep it together. Okay, hence the minus sign. Where all of those constants, the 4 pi squared and the strength of that factor, are all combined in this term C2. So C2 has the units of energy, and it's just a term that I need to determine basically later. Let me explain one thing about this law. This is not a theoretical law. This is not a fully experimental law. It's really a semi-empirical law. In other words, you determine things based on physical arguments, based on theory, and then you go later to the lab and test them and fidget, basically play with the numbers to model the real behavior, the real stability of the nucleus. So it's not really a theoretical law, and it's not completely an empirical law. So it's an experience or experiment driven by theory. So that's basically what this whole law is. So that's what he proposed. And you will see that it fits the bill beautifully. And then the third term is actually Coulombs force. So this is actually the one that I described in here. Okay, barring that constant, which is E squared, which is just 1.6 times 10 to the negative 19 squared, divided by 4 pi epsilon naught, which is just a 9 times 10 to the power 9, another constant. I have 1 over R in here in the denominator. And remember, R is proportional to A. So it has R naught, but it's also proportional to A to the power 1/3. We just looked at it again. So it has A to the power 1/3 in it. And it's coming from this expression here, the argument about the density. So the denominator has A over the mass number over 1/3. That's basically what the Coulomb force is. It says 1 over R. But look at this term, the numerator. How many protons am I talking about? I'm talking about Z protons interacting with one another. And again, from physics too, if you guys remember, if I have a bunch of particles, charges, Q1, Q2, let's say, for example, I only have 2. In this case, I only have 1 interaction between them. So the potential energy in this case is just 1 over 4 pi times epsilon naught times in this case, Q1, Q2, over the distance between them, which is between 1 and 2. So this is R on 1 and 2. But if I have a third particle in here, then the number is not just 1/4, actually it's going to be 3 in this case. So I have Q3, so it's going to be the distance between 1 and 3 and the distance between 2 and 3. So the potential energy I have to add to it 2 more terms, 1.4 pi epsilon naught Q1, Q3, over the distance between 1 and 3. And I have to add another term in here, which is 1/4 pi epsilon naught times Q2, Q3, divided by the distance between 2 and 3. So this is the potential energy now when I have 3 particles. When I have 4 particles, the problem gets complicated more. So if I have Q4 in here, sitting in here, I have to take this interaction, I have to take this interaction, and I have to take this interaction also. Okay? So in this case, I will have 1, 2, 3, 4, 5, 6. The formula for it really, if you guys remember from physics 2, it's 1/2, and I will tell you exactly where the 1/2 is coming from, times the sum over all j's from 1 to n, if I have n of them, and let's use a different n, lowercase n, because we have the number of protons in this case. And also I have to sum from I equals to 1 all the way to n, where I cannot be equal to j. I cannot take Q1, Q1 or Q2, Q2. So the 2 particles cannot be the same. Of course, 1/4 pi epsilon naught times the Qi, Qj, divided by the distance between R and J. Okay, so that's the general term in this case. Okay, if I have n particles that are interacting, so this is the potential energy for them. The 1/2 is necessary because in the summations I start from 1 to n, and in here I start from 1 to n also, where I'm imposing that I and j cannot be equal. So I have to skip those terms because then I'm dividing by 0. Okay, I'm going to count double. Why? Because at some point when I start with 1, I'm going to include 2, 3, 4, 5, and so on and so forth. But when I go to 2, I will have to start again from 1, and I already did 1. So I can go from 3 and so on and so forth, but 1 is already done. But this summation assumes that you don't have, you can go through all of them. So you really have to divide by 2 to eliminate the doubles. So that's where the 2 is coming from. So here is the deal. I have, when I count one of them, I have the others minus 1 because I am starting with 1. So if I count one of them, I'm already counting the other. In other words, let's say I have Z protons. One of those protons is being repelled by Z minus 1 other protons. So I have, for every proton, I have Z minus 1 interactions. But how many protons do I really have? I have Z of them. I don't have 1. So I have Z times Z minus 1 repulsions. That's really how the counting is. And if I'm careful enough with these calculations and I do my summations in here, and if all the masses are the same, so I'm going to pull them out, and all the distances are roughly the same average distance, I'm going to pull it out. So this term becomes just 1/2 of E squared over 4 pi epsilon naught times some R average, not R squared. So this is an average distance between all of them. Granted, some of them are very close from each other, and some of them are very far from each other. So what I'm saying in here, just average the distance between them, because it's going to be of the order of a femtometer anyway. So it comes out. Then what I'm saying in here, just sum all of the integers from 1 to n to z in this case, and all the integers from j equals to 1 to z, when I'm imposing that I cannot be equal to z. So the first summations will give me z of them, and then the other summations, but don't forget the factor of half in here, the other summations will give me z minus 1, and that takes care of all of the terms in here. Obviously, I will have, at the end of the day, some constants, a bunch of them, so I'm putting all of them in this C3. So this term is coming from the repulsion. It's trying to tear the nucleus apart. So it's not really adding to the binding energy, but it's taking away from it. So these three terms should have no problem understanding them. The first one is the volume contribution, which is positive. That is really what is adding to the energy of the system. The second one is actually taking away from its strength to flatten it, and that is the surface tension, due to the fact that we're giving it some sort of a spherical shape, okay? The third term is coming from the Coulomb repulsion. I have Z protons interacting, each and every one of them with the rest Z-1 protons, and divided by the distance. In this case, the distance has some R naught, but then it has A to the power 1/3. So that depends also on the mass number. So I have this term in here. Now, what's up with this term? Let me draw the graph so that you can see exactly what I'm talking about in here. This is experimental data. This is the NZ graph. The NZ graph. If I plot on the z-axis, on the x-axis, Z. So this is the number of protons. Okay, on the y-axis, I'm going to plot N, the number of protons, the number of neutrons, I'm sorry. Well, if you do, first of all, this is the line N equals to Z. So this is the dividing line, okay? Now, the stability line matches with up to Z equal to 40, and N equals to 40 in this case, around this number, matches the N equals to Z line. Then it starts to deviate from it, but not by much. So this is the stability line. As the number of protons increases, the repulsion starts to become bigger and bigger between this, because as you jam more and more materials, some of these protons that are at the outer edges become far away, where this force drops. This force, as I was saying in the beginning, does not have much effect at all as you move away. So at that point, the interaction is dominated by the repulsion. So this term starts to repel one another. So what you need to do to fix that, you need to throw in more and more neutrons. So more and more neutrons then will add to the stability of this nucleus. So for heavier elements, for elements that have big Z's, you really need more protons per nucleon compared to the number of protons in order to keep it stable. So this is the stability line, and it starts to deviate for larger and larger. So more protons are needed in this case for the elements to become stable. So this is the stability curve. So what's going on in here? For low mass numbers, for low Z numbers, first of all, this term in here is N minus Z, so that you can see, because N minus Z is, because A is equal to N plus Z, just move N and write it as A minus Z. So in this case, N minus Z, the difference between the protons and neutrons is exactly A minus Z minus this Z. So it's A minus Z. So this A minus 2Z. So this is basically the difference between the protons and neutrons. Okay. That difference. For less mass numbers, if A is small, you don't want that much difference, because if it is, that is going to contribute with a negative number and adds actually to the instability of the nucleus. You want them to be as close as possible from each other for low A. For large A, though, it doesn't matter. This term in the denominator will kill this difference, okay? It's still not good. Actually, the difference is still very close from N equals to Z. I mean, I exaggerated a little bit in the picture, but you are permitted there to add those things, because it's not going to harm. As a matter of fact, it's going to help, as I was saying in here, the binding this proton and this proton, they're far away from each other now. They don't attract each other through nuclear forces, but actually they repel each other through the electrostatic force. So in this case, you need to throw in a little bit more protons, more neutrons, I'm sorry, that don't have a charge to keep them from flying, okay? So that, in a sense, explains why the mass in nature, you cannot find more than Z equal to 92, which is uranium. Uranium is 92. You can't have, and nature was not able to provide for us. And even the ones that you create in the lab heavier than Z equal to 92, they are most of the time short-lived, and they're not stable. Okay, so in terms of stability, they are not that stable. So this term in here is critical to explain the NZ graph. Okay, so this term in here, there is as the nucleus starts to grow bigger and bigger, you would want it to stay stable. In order to do that, you put a little bit more of the nuclear force near those protons that are repelling each other, okay, at the edges. But the protons near each other, they're going to attract. Yes, there is a repulsion, but the repulsion is small by a factor of 137 compared to the nuclear force. So at those points, they're completely stable. So for example, if you take the helium atom that has 2 protons and 2 neutrons, so the helium atom looks like this. There is an attraction between all of them due to nuclear forces. All 4 components, they're attracting one another due to nuclear forces. Yes, there is a repulsion, but that repulsion is negligible, is of the order of less than 1%. So this is why the helium, in this case, 2,4 is very stable. Okay, it's actually on the periodic table also is one of the inert gases, so it's not going anywhere. So this is but for bigger volumes, for bigger, basically when A starts to grow, then in this case this relationship becomes a problem. So this is what is it? The Segre graph is the one who proposed it. But this is the NZ graph, and it's really, this is from experiment again. And as I was saying in the beginning, this is a semi-experimental, semi-empirical law, okay? And the square there is coming from the experiment. Really, what we're looking for is just the difference. And it turns out it's the absolute value that matters, okay? Not the actual physical value, which brings me to another point that I mentioned briefly right now, namely the isotopes and the isotones. The isotopes have the same Z. So if I look at this curve in here, there are some elements outside of the stability curve that are actually on each side of the stability curve. So if I follow the stability curve, there are some elements that follow the stability curve. Obviously, they are not as stable as the ones that are on it, but they follow on it. So this curve has a little bit of widening on both sides. If I travel from top to bottom, those are my isotopes. They have the same Z. So those are my isotopes. But if I travel on the vertical axis, so in this case, I have different Z's, but the same N. The same N. So those are actually my isotones. Okay. There is some curve, if you study it carefully, there is some elements that seem to have fewer, I mean, that they pass through certain numbers in here. So if you draw cutoffs at 20, 40, and so on and so forth, you will see that there are some elements that seem to be have more stable isotopes than others. Okay, so there are a little bit of relationships in there. As a matter of fact, brings me to the next term in here in the curve. And this term in here, actually the book had plus or minus. I added a 0 because it's important. And actually in the book also, if you follow it, you will see that actually a 0 is needed. Let me explain about this term. This term could be positive. It could add, could strengthen your binding energy, or it could be negative. It could be not good, so you're going to take away from it, or actually it could be completely not there. And you asked me about the power to the negative 1/4, that is actually due to experiment. Okay, so again, the C5, C4, C3, C2, C1 are all basically trying to model this behavior, the one I drew now for the stability curve, and also trying to understand what's going on in this curve. And there is another concern that is going to pop up immediately coming from Schrodinger's equation. If I model my nuclear force using the expression that I was telling you earlier, namely if R is very small compared to R naught, then in this case, I want it to be actually a repulsive force. If R is very big compared to R naught, what I mean by that is few values, only about 3 values of R naught, then this nuclear force drops to 0. So the only thing I'm left with is the electrostatic force, which is repulsive. Or between the protons only. So the others, they don't play that game at all. The neutrons, they just watch that, okay? And then if R is around R naught, this needs to be stronger by a factor of 100, 137 to be more specific, the alpha factor that we saw a long time ago. When we model that, this is what the picture looks like, basically. The masses of the proton and the neutron are almost the same thing. So it looks like for every nucleus, as I start building up my model, I have energy levels in here, similar to the energy levels for the elements. Remember, for the hydrogen atom, that depends on N. Okay, so that's similar in a sense. As I put my first proton sits in here, so it's going to go to this energy level. The next, a proton, obviously there is another force that comes into play. It will not allow it to be there. It's going to convert it to a neutron, and that is actually the weak force. Okay, you cannot really have 2 protons next to one another forming a bonding. So in this case, you will have an isotope of hydrogen called deuterium. Okay, that's force. Obviously, I draw them on the same level. They are slightly off, but it's negligible, the difference between the proton and the neutron. If I bring another, proton, I could have a proton in here, which is an isotope of helium, or I could have a neutron instead in here being converted to a neutron, and then I will have another isotope of hydrogen, okay? But the next element in here is the next nucleon in here is going to be a neutron. So in this case, I have helium. Well, I have 2 protons and 2 neutrons. This is the mass number, by the way, which is just Z plus N. So in this case, it's stable. It's actually a stable. The spin of this one is up. The spin of, remember, they are fermions. Each one of them has the spin 1/2. This one is spin up. This one is spin down. And this is one of the most stable elements, stable nuclei there is. Okay. So helium, just like when you look at the periodic table and you look at the last column in here and you see them, the inert gases that are characterized by the numbers Z equal to 2, Z equals to 10, Z equal to 18, the number of electrons in this case, okay, because the periodic table is really based on the electrons. There is actually also similar pattern that seem to have developed based on solving Schrodinger's equation using this model for the nuclear force and the electrostatic force. If we solve it, we will have different models in here where the elements that have the Z equal to 2, 8, 20, 28, what is the next one? 50, and then 72, or not 82, and then 126. Those are the most stable elements that have actually a total spin equals to 0, okay? And that seem to fill all the energy levels. Similar to the shell structure and the atomic model, this is exactly what's going on in here. So these elements have the most stable nuclides. Okay, so those are the elements in the periodic table, at least in terms of the nuclei, the most stable ones. Obviously, the first one is so this one is actually helium described. This one is actually oxygen. Oxygen has a 8 protons and 8 neutrons. All of these numbers are called magic numbers. Just like when you think of in the periodic table of the noble gases, inert gases, these are called the elements, the nuclei with the magic numbers, okay, when they have these Z numbers. As a matter of fact, here is the deal. Some elements are doubly magic, okay? So what I mean by that is, like, this one is doubly magic, this one is doubly magic, the oxygen and some other elements in the periodic table. This element has not been seen in nature. Okay, when Z is bigger than 100 than 92, so this element doesn't exist in nature, but all of the other. This is actually lead, and lead has so many isotopes in here. And if you look at the radioactivity of the heavier elements, most of the time they end up in lead. Once they end up in lead, that's it. That's so they reach their stability. So this is lead. Okay. So these are some of the questions in here that really beg to be answered. Here is the deal. If Z is odd and N is odd, this is unstable, with the exception of few elements. All of the elements are unstable. Okay, so in this case, I have to put a minus sign in here. What is my expression in here? I have to put the minus sign in there. If so, this is another condition. Z is even and N is even, then in this case, it's stable. As a matter of fact, this is one of the most stable ones. Stable. Okay. Again, there is exceptions to the rules. Out of the 25 or 3,500 elements known, what is it, 2,500 elements known, only a few hundred, about 300 that are stable. All of the elements, they really have all kinds of radioactive behavior, which is the next topic, the next topic that we need to discuss. Anyway, so these are stable. So in this case, actually, it adds to the binding energy. So you need to use the plus sign. So this is a minus sign. And this is the plus sign for the last term. Now, if any one of them is odd, if any is odd and the other is even, what I mean by them I meant Z and N. Okay, any one of these two is odd and the other is even, then in this case, you don't add the term altogether. It doesn't come in at all. So you just put a 0 there times whatever you have in there. Okay, so in other words, don't count it. Okay, don't count this one if the number is of N and Z are both of them are. Makes sense so far, this expression to you guys? This is a model again. This is not a theoretical law, but at least where each term is coming from. Yes? Makes sense to you guys?
Yes.
Okay, very good. So the first term is due to the attractive force, and that is a volume behavior. That is the main one, actually the one that keeps the entire nucleus stable. Then you have the surface tension, which is trying to flatten the nucleus. So it's actually a negative contribution. It doesn't help in the binding, it actually takes away from it. Then the Coulomb force, which is a repulsive force between the protons, must also be included. And it's actually not helping, is actually trying to unstabilize the nucleus. And the third term, which is coming from the difference between the protons and neutrons for larger nuclides, that becomes critical because you need to inject more neutrons to keep it stable. But what prevents you from injecting a million of them? There is no limit, actually. If that's the case, then just keep on throwing neutrons, and you keep on throwing. It doesn't matter how many protons you have. So technically, you could do that. You could inject as many neutrons as possible. But there is a problem. The curve leaves you only with a small difference only. So that's why you have to have only just a small number. So if you keep on increasing that difference, that gap, then in that case, that negative term starts to take away from the binding. So that's what the experiment is telling you. That's why you can't really have a huge Z. Z is limited in nature up to 92, because then after that, there is a limit on how much energy you can put in. So that's really what the whole discussion is. So that's really the fourth term in that expression. And the last term is actually due to the shell structure that seems to give me some sort of stability, stable elements where both N and Z are even. In this case, I have a spin 0, and that is really the most stable configuration, if you wish, or more stable than any. So that actually adds to the binding energy. If both of them are negative, actually, with the exception of about 4 elements in the periodic table, all of the others, not the periodic table. When I say elements, I mean in this case, I don't mean the periodic, because I'm including isotopes, which are not included in the periodic table. So only a few elements in this case that are stable, and the rest are not. So when N is odd, N is odd and Z is odd, then in this case, you better include the negative term to account for that factor. And then finally, if N and Z are both even and odd, then in this case, more or less it cancels on each on average. So I include the 0 in there. So this is the model that we emerged with for the nucleus in order to understand how it is, what keeps it together, and what keeps it from basically flying every which way. So this is the model that we're going with. And I think we covered enough about this. Oh, yes, the constants. Okay, C1 is of the order of 15, 16 mega electron volts. All of them are energies, by the way, because we took care of the, these are dimensionless numbers, Z and A and all of that. So they are dimensionless numbers. So it matters in this case in terms of the energies, C1, C2, and they're all in mega electron volts. Their values are determined by experiment to do good fitting for these curves in here, okay, to understand these curves. So the curve that I was referring to is on page 1453, okay? And the elements that have an odd number of Z and N and that are stable are, of course, one of them is that isotope I mentioned of hydrogen, namely H12. This has 1 neutron and 1 proton. The other one is lithium 36. Again, it has 3 protons and 3 neutrons. The other element is a boron 510. It has 5 protons and 5 neutrons. And the last one is sodium, nitrogen 714. Again, it has 7 protons and 7 neutrons. Note that all of the numbers are actually small, okay? All of the numbers are small, which are actually being helped a lot by this factor again too. So they're so those are the only exception to the rule. Only 4 elements that seem to defy this rule, okay? This rule, I'm sorry, okay? So other than that, all of the others, and as I was saying, this is semi-empirical law. So trying to explain it in terms of this. What's in here. Brings us to the last point of this chapter, and that is the radioactivity, and the lab is going to be on it. So okay, so radioactivity was a phenomenon that was actually formalized and discovered toward the end of the 19th century, where we noticed that there are particles that seem to come out immediately out of the elements on their own, and they seem to change the chemical properties of the elements. Some of them do, at least, when you have in the case, for example, of alpha or beta decay. So based on their power of penetration, they gave them different names. So you have the alpha particles that are the least penetrating materials. Then you have the beta particles, and then you have the gamma particles. Gamma particles are very penetrating, okay? So that's basically what it was until later on when we did the experiments using basically the same thing like J.J. Thomson, what he did to discover the electron. When we scatter them on a magnetic field, we saw that this ones have a positive charge. As a matter of fact, it has positive 2e charge, twice as much as a proton. Okay, twice as much of an electron, except the opposite sign of the electron. And also they have a mass number that is of the order of basically 4 times u. So this is actually the nucleus of, oh, why did I put the plus sign on this side? It's a positively charged nucleus. So this is the nucleus of helium actually, okay? It has 2 protons and 2 neutrons. That's what the alpha particle is. So in the beta decay, we have actually 2 types of beta decay. One that emits an electron and one that emits the same mass as an electron, except that it goes in the same direction as that of the alpha particle. So it's a positively charged value. And the value of E is the same. And the mass is that of an electron, which is 9.11 times 10 to the negative 31 kilograms. Okay. So that is actually, this one is the normal electron. And this is a positron. So from this point on, we can call beta minus and beta plus, if you want to call them, decays, okay? Because this one is always charged positively, okay? It's twice E. But this one, sometimes you have an electron, sometimes you have a positron, okay? Particle that later on was given the name of a positron, which is a positive charge. This one does not have a charge. And the mass does not have a mass too. It turns out to be just, this is actually an electromagnetic radiation, EM radiation, with very high frequency, okay? In other words, if you run the gamma, if you have a material that emits gamma decay, and then you run it through a magnetic field, it does not deviate, it goes straight out, okay? It does not go one way or the other. This one will bend, and the bending in here is less than, because it has more inertia than the bending of this material in here in a magnetic field. That is going up or down. This is positron, this is an electron. So that's basically how the experiments led us to this decays. Okay, so what's going on in terms of inside the materials? In terms of the alpha particle, you have an element in here, and then spontaneously, it's going to emit an alpha particle. Okay, so this is your alpha particle. So what happened in here? So Z has decreased by a factor of 4. So whatever you had before, so if you have Z in here, Z went down by 2. The mass number in here, whatever you had in here, it has decreased by, A. So the mass number A has decreased by 4 actually, because you lost 2 protons and 2 neutrons. So every element that goes an alpha decay will have it will change completely to a different element in the periodic table. And it goes down on the periodic table to the left by 2 digits. Okay, plus the alpha particle. So if you look at the periodic table and you're given an element, no matter which, and it goes back, if it goes through an alpha decay, it's going to move to the left, okay? Because its mass number, its atomic number has dropped by a factor of 2. So this is basically what we know about it. Now, for one that goes through a beta decay depends. Beta decay, in this case, the element, if it is a beta minus decay, normal decay, so an electron in this case, well, there is another problem in here that we're going to discuss quickly, okay? In terms of mass, because the beta decay had the problem in terms of the distribution of the energy. When you compute the energy before and the energy after, it seems like it's going through a spectrum of values, okay? It's not going through the normal quantization in here if it's just an energy that is in quanta. So there was a problem with it, okay? The only explanation for it is there must be another particle that has its own kinetic energy and it's moving with different directions. Also, the conservation both of conservation of energy and momentum both seem to have been violated by the beta decay until people gambled on the conservation as it must be true, and that there is another particle. And sure enough, that particle in this case, which is the antineutrino, was discovered later on. Okay, and it has the right properties to make this whole thing work. Okay, so this particle that was posed later on existed, was based on experiments. So this is actually a neutrino, but as a matter of fact, in here I really don't need a neutrino, I need an antineutrino. Okay, and we'll see why that is. Actually, chapter 44 will go in depth about this topic. So what happened to the Z now? Well, it seems like the Z has increased by a factor of 1. What happened to A? A does not change. So it looks like what's going on in here is that a neutron, remember A is equal to N plus Z, a neutron has been converted to a proton so that Z goes by a factor of 1. So that if I add the 2, A stays the same. So one neutron under the beta decay will go to a proton. That's basically what this number is, plus an electron. Let me write it as an electron in here, plus a neutrino, in this case, that does not have a charge. So this is positive charge, this is a negative charge, and the charges cancel, so there is conservation of charge. So initially, the neutron has no charge. Now the neutron, the combination has no charge. And also, the nucleons, I had one nucleon to begin with. Now I only have one nucleon because the electron is not a nucleon. So this is called the baryon number. So I had one baryon number equal to 1 before, and one baryon number equal to 2, 1 equals 1 at the end. And then since there is an electron in here, an electron is not a baryon, by the way, it's coming from chapter 44, it's a lepton. And now I need to cancel that lepton because I did not have any leptons to begin with. So I have to have an anti-lepton to cancel it. And this is actually an lepton, an anti-lepton, because I have the anti-version of it. And it's of the type E because this is an electron. So this is really explains the conservation of everything. Okay, so this is the beta minus decay. How about the beta plus decay? The beta plus decay, it's the opposite, okay? Where A stays the same and Z decreases by a factor. So what happened in here for the beta minus decay is that the element will migrate to the right on the periodic table because its Z increases, okay? But for the beta plus decay, it's the opposite. It's going to migrate to the left again by a factor of 1. So in the beta decay, again, an element, a beta plus decay. So it's going to be the same element, except now I have, let's not worry about Z later on. So A does not change in either case. Okay. Plus, I have a beta plus now, plus I need a neutrino now, not an antineutrino, because positron is an anti-electron, and that takes care of the anti-lepton. And so this is the lepton now that cancels, so that there is no leptons at the end before, because we did not start with them. So now I have a charge that is positive. So the charge in here has to decrease by a factor of 1. In other words, this is the other way around. So Z has decreased by a factor of 1, and the number of protons has increased by a factor of 1, so that A stays the same. So in this case, it's Z. So Z has decreased by a factor. So I'm going to the left in here on the periodic table. So what looks like is going on in here is that a proton has been converted to a neutron plus an anti-electron, which is called a positron, plus a neutrino, a normal neutrino. Okay, so we have conservation of everything. So if you're worried about a baryonic number, this is 1 and 1 after the reaction. These are 2, both of them are equal to 0 in terms of baryon number. In terms of a charge, this is a positive charge, and this is a positive charge. So I had positive E and positive E at the end. In terms of leptons. I don't have any on here before, so I don't have any in the end because this is the anti-lepton and this is the lepton and they cancel each other and I have 0 at the end of the day. So everything looks like it's working. So this is the beta plus decay, okay? Well, this can only happen in at least so far we know it happens inside the nucleus and the nucleus only. And we will try to understand it from chapter 44, what causes this process. And you will see that there is another particle that comes into play called the W bosons, W plus, minus, or 0 bosons. Okay. And we will try to, again, this is chapter 44. Okay. So for right now, don't worry about the details of how this happens, but the process, the same thing for the other one. And the same thing actually, so this one is that, but this one also, what is it? The other one also involves the, this one, yeah, it all involves the weak force, okay? Anyway, the last process, also another type of beta, beta, if you wish, another decay, involves actually electron capture. And this is an important process. So what you have in this case, you have a proton captures a normal electron, and at the end of the day is going to be a neutron, okay? Plus, in this case, a normal neutrino. So this is called an electron capture. So what's going on in here in this case is a proton, a neutron, and proton and electron, they fuse with one another and they form a neutron. Again, if you're worried about the positive the charges, this is a positive charge, this is a negative charge, and this one is 0, and this one is 0. So I don't have any charges at the end of the day. So 0 equal to 0. In terms of the baryons, I have 1 and I have 1, so it's 1. Okay. In terms of leptons, I have 1 and I have 1, so everybody is happy in this case too. So everything is fine. So this nuclear reaction too. So this is the electron capture. Why this is important? Because stars, as they evolve and they become big and massive and everything else, and they grow and they expel all of their oxygen, I mean their energy and their hydrogen changes, and they go through their entire life cycle. And if they're big enough, not too big though, because if they're too big, then they could collapse into a black hole. So there is an intermediate stage where they don't just go into a white dwarf, actually they become a neutron star. So what is a neutron star? All of the electrons that existed in the star from before, they basically start to fuse with the protons, in addition to the existing neutrons already. So that fusing between the two, basically the protons start to, because of the tremendous pressure from the gravity of this collapsing basically star, they start to fuse with one another and they become neutrons. So that's why they call neutron stars. Through this process, okay? So that's how the neutron stars form. And the last one actually is easy to understand. So you have an element. So this is the gamma decay. So you have an element of a given number Z and a given number A that is not stable. So the instability is written by A. In other words, there are two probably protons next to one another, and or three of them next to one another, and another one far away. So what happened in this case, they rearrange themselves only to minimize the energy. That's all. So it's the same element plus gamma rays plus energy. Most of this energy that is coming out through, in this case, it's probably it takes energy. But if it's coming out in terms of kinetic energy for these particles, this one is actually pure rays, pure gamma rays, pure radiation at very high frequency. Why is this element is not stable? It's because of that model that I was describing from before, this one. So you have the same number of protons and the same number of neutrons, but they're not sitting in the proper energy levels. So for example, some of them are here and one of the protons is here, and one of the protons, for example, happen to be here. So we have in here a normal neutron in here. So this is excited, so it wants to go back into normal state. Okay, it decays that gamma ray. Or the proton or the neutron actually probably ended up in here too. So this one also will emit this much gap in energy, which is twice the gap times. So that's basically what I'm talking about. So if this is EG, so the frequency in here is going to be, for the case of this neutron, is going to be twice EG divided by H. That is the frequency that is going to be emitted. Okay, the frequency of this one. So you can find the wavelength that corresponds to that one. Okay, so again, this is I just use E, the energy equals to H times frequency. Okay, one of the earlier expressions that we saw when Mr. Planck used it to find the energy of that. So this explains a lot of the processes that we see in nature and its radioactivity. One of the key factors in here, and it's relevant to the lab, is radioactivity. Yes, it's driven by that weak force, and we'll try to explain it down the road with chapter 44. But it's actually a probabilistic or a statistical phenomenon. Meaning, if I have a given element and I'm watching it, you can tell when it's going to go radioactive from any of those. Now or wait later or wait later. So it's a statistical phenomenon. We don't know, but we know the average. So this brings us back to the idea of chapter 18, actually, when we did the kinetic theory of gases. So this is similar. So this is a probabilistic theory and uses probability trying to understand the behavior, but as a global material. So if I take 1 kilogram of a given material, then I can describe that behavior on average and come up with laws. So here is the law. The rate of decay is proportional to the initial mass. Okay, so what I mean by that, if I start with N naught, with N, okay, so N naught is the beginning, yes, but at some point I'm down to N, okay, and at later a time I'm going to probably be down to 0, okay. So the element that we start with the exception of the gamma rays, usually is different from the starting one. So the first one is called the parent, and the second one is called the daughter. That's by convention, okay? So the same thing in here. These are processes inside the nuclei. So in this case, this is an element, this is the parent, this is the daughter. And it can have the daughter become a parent. So then you can have a parent which has daughter, and the daughter has other daughters, and so on and so forth. So it's going to spread. So this is not a process that ends with just one decay. It could go through several decays, like in the case, for example, of any of those elements that you see in the periodic table. They go through a lot of pattern. And as they do, depending on what type of decay you have, they migrate through the periodic table. And as I said before, for example, lead is the stable element for a lot of these decays that end up in it, okay? So the point being in here is that the daughter and if I keep track of the parent only, I don't care about the daughter or any of the derivatives after that. If at some point I have n, the rate at which n drops, meaning dn over dt, is proportional to the number n, number one, and it's characterized by the value lambda. Since this is a drop, dn over dt is equal to minus lambda n. So the minus in here, it's because it's a decay. And lambda is characteristic, meaning each element, this is coming from probability if you want to analyze this problem, basically, and coming up with the properties of the elements in there. So we're not going to go there, but the point being in here, this is the rate at which this one is dropping. Another expression that I can define is the activity, and the activity is how much we're dropping. So the activity is this ratio in here. So the activity, I could define it as being dn over dt. So if I take the derivative of A with respect to T, how much the activity is dropping. Again, dn over dt is just this whole number. So it's going to be minus lambda times dn over dt. And this is actually A. So it's the same expression, whether I take the first derivative or the second derivative. And that are the properties of actually the exponential function. So in other words, the solution for this differential equation for the activity. So this is the activity, by the way. Okay. So in other words, how much radioactivity? So if I bring a Geiger counter, Geiger-Müller counter, and I start counting the radioactive materials that are coming out, I see probably in the beginning a lot of activity, a lot of ticking, basically, and then at the end starts to drop until basically it goes down. So that's really most of the time what we're worried about. So if I solve this differential equation, it's simply equal to a constant times exponential of negative lambda t. Now, this constant is A naught. So this is the beginning activity, or in the case of N, it's N naught. So A is equal to A naught times exponential of negative lambda t, or N is equal to N naught times exponential of negative lambda t. What N naught is the initial conditions, basically put t equal to 0, A is equal to A naught, the constant is that one. You guys did differential equations like this one, didn't you? No? Or in physics, actually, a lot. Make sense?
See.
Okay, I hope that means yes, okay?
It does.
Okay, yeah. Anyway, the point being in here is, so this expression in here gives me the activity. So N naught is this point in here. So anytime in the future, I can predict when this one goes, how much basically N I'm left with. Here is the point though, okay? This is one of the labs I miss actually on campus because it's fun. Here is by definition, T1 half-life is when N drops by a factor of half, okay? So it drops to 1/2, to 50%, basically. You start with 1 kilogram, you're down to 500 grams. So in that case, basically, that's the time it takes for it to go that long. So in this case, all I have to do is just put N equals to N naught over 2 equals to N naught times exponential of minus lambda. I'm going to call this time T1/2 because everybody calls it that way. Cancels the N naught. Take the log, the natural log from both sides. This gives me a natural log of 2 with a negative sign because it's in the denominator. This is negative lambda times T1/2 because I took the natural log, okay? Cancel the negative and the negative, and from here I can get an expression for how much T1/2 is. T1/2 is simply equal to ln of 2 divided by lambda. So lambda is actually characteristic of how long this material can last, basically. Okay, ln of 2 is 0.693. Everybody knows that. Divided by lambda. Okay, so this is basically the expression that we have for it. Another, is it correct? I'm just talking nonsense in here, as if I know it. Okay, ln, oh, log, they don't call it ln in here, log of 2. Yeah, 0.693, good, okay. So this is T1/2. Another term in here that is used is called the lifetime. And that is basically when N drops by a factor of E, 2.71, about 1/3 basically. Drops to a factor, 2, not by, 2. Meaning N at the end is equal to N naught over E, okay? So I'm left with almost 1/3 of it. So in that case, that will happen at T equals to, do they give it mean? Yeah, I think they call it T mean, okay? So it's going to be exponential times N naught exponential of negative lambda times T mean. Okay, if I take the natural log, and here n naught time n naught cancels first of all, and I have 1 over e equals to exponential of negative lambda T mean. Again, take the natural log, or it's clearly this one is equal to 1, exponential to a negative 1. So that means that lambda T mean is equal to 1. That means that T mean is simply equal to 1 over lambda, okay? Which is from that expression is T1 half over 0.693. So it's slightly more than the T1 half, okay? And that's expected because you're going from 1/2 to 1 to remaining, basically consuming 2/3 of the material. So you start with 1 kilogram, you're down to about 340 grams or something like that of the material. So that is the lifetime. So that's by definition what the lifetime is. So these are basically the extent. The math is not really hard in terms of this one, of this thing in here. In terms of applications, we use it in biology. We use it in carbon dating because we know carbon is used for. Actually, we use it for radiometric dating completely. We use it for example, how old is that's how we determine the age of the solar system and actually the age of the Earth because of the radioactive materials. Some of them are in the billions of years, like potassium, for example, and some of them are actually in only a few thousand years, like carbon-14. And carbon-14, for example, is a material that is in the air coming from the cosmic radiation that hits the atmosphere on a regular basis. So there is a concentration of it in the air versus that of the normal carbon-12 that you see in nature, in the ground. That is the most stable of the two. Now, when a plant takes in the air in this case, and so it's a nitrogen for 7 basically that is converted to carbon-14 from the cosmic radiation. So that carbon-14 again goes into the plant, and now the plant consumes it, and it has the same ratio basically of carbon-12 to carbon-14 as that of the atmosphere. Now, when the plant dies at that point, there is no more, it does not take any more carbon-14. So all of its carbon-14 starts to go through the cycle to become carbon-12. So if I have a plant, an old one, and I see what is the ratio of the carbon-14 today on it versus carbon-12. If I can find that ratio, and let's say, for example, it's exactly T mean, I mean, it's that ratio is about 2/3, or I'm sorry, 1/3 of what it should be. If it's 1/3 of that to what it should be, then that plant has been dead since T mean. And for carbon, it's about 7,000 years or something like that. So I can determine how long ago this plant died. And of course, any animal that feeds on the plant, or animal that feeds on the animal that feeds on the plant, that too will have the same concentration of carbon-14 in its system as that of the atmosphere at that time. So if I find bones, for example, of humans or animals, and if I can take how much carbon-14 they have right now versus her carbon-12, then I can reverse engineer the equations and find exactly how long ago this animal died and stop taking more carbon-14. So that is using carbon-14. Similar fashion, also we use it for dating in terms of geology and other processes that involve other radioactive materials. So this is the entire chapter 43. Okay. Oh, I'm sorry, still have to talk about fusion and fission. So still have about maybe 15, 20 minutes. Especially we're going to talk about the proton-proton cycle in the sun. And again, we really are not going to learn new formulas in them so that you guys know, just for your information, how these processes happen. Because the binding energy, how much energy is released, we covered all of them and so far. And so we're ready actually to go to chapter 44. But before I do that, I really need to talk about fission and fission and fusion, and especially in terms of fission, that it is used in the industry to make energy out of it right now, or make nuclear bombs. That's one of its applications also. And the nuclear fusion, the nuclear fission actually is used to make bombs, but actually sometimes combined with the fusion to make hydrogen bombs. So we're going to talk about the critical mass and how that happens. And then also we're going to talk about the proton-proton cycle in the sun. And maybe we can even touch on the CNO cycle in the stars in general. And that closes chapter 43. Sounds good, everybody?
Yes. So you're gonna finish it on Thursday.
On Thursday, we can finish the nuclear reactions.
Mhm.
And that's the end of this chapter. Then we're going to introduce big time. We're going to dive probably midway in chapter 44 to talk about the stuff that is relevant for the standard model, because we will get to a little bit of QCD, quantum chromodynamics, okay? And try to understand the physics of color, basically. Not in that color in that sense, it's a different kind of color. And try to understand what makes the proton and neutron, try to see other elementary particles as we go along. So that's chapter 44. And then we're going to end it with basically how the universe came to be, okay? And where is it going to end up? So that's really a big task that is from chapter 44. Sounds good, everybody? Sounds exciting?
Yeah, I'm super excited.
Okay. Okay, guys, I'm going to stop the recording and I'm going to see you guys on Thursday.
Have a good day.
You too, bye.